Hello, and welcome to the second to last unit for pre-AP chemistry. So we only have one more after that. So we're getting very close to the end of the school year. So this unit is called Oxidation Reduction Reactions. And it is basically, we've seen these reactions before, we just didn't know that's what they were called. And they are reactions in which electrons are being transferred between the reactions. And we'll get to the definition in a minute of what they mean, but they have to happen together. You can't have one without the other. And so basically, before we decide what the definitions are, we have to be able to decide assign some oxidation states to these, and that's what we're going to do in today's lesson. And then we're going to define what is oxidation and what is reduction. From here forth, I will refer to these as redox reactions because it's shorter, and that's what most people call them. And then when we're looking at redox, what are they? Like I said, we've already seen them. We studied these 5 types of reactions at the end of last semester: synthesis, decomposition, combustion, single replacement, and double replacement. And of those 5 types of reactions, the first 4 are actually what we know as redox reactions. And we'll see what that means in a little bit. Okay, so let's continue forth with how do we assign an oxidation number. First of all, what is an oxidation number? Well, it's kind of like a charge, like an ionic charge, but not exactly. Okay, so we have these arbitrary rules that we're going to look at in a moment, and we're going to assign each element in a compound, regardless of whether it's ionic or covalent. We're going to assign them either a positive or negative number based on what they are bonded with. Okay, once we assign that oxidation number, it can be used to determine whether that element is undergoing reduction or oxidation, because of what it turns into on the product side. Okay, so unlike ionic charges, they do not have a physical meaning. Although we will see that oftentimes something's oxidation state or number, either one, is the same as its ionic charge. So that makes it easy. Where we run into a problem is our transition metals and our non-metals. They can do a variety of things, and so we'll be able to look at those and figure out what they are based on our set of rules. Okay? And just a side note, oxidation number or oxidation state is the same thing. I tend to say oxidation states because that's the way I learned it, but it is also an oxidation number. So either word is acceptable. Okay, so here are those arbitrary rules that we talked about. And I will tell you that this is important. These are in order of importance. So in other words, rule number 1 trumps rule number 2, which trumps rule number 3, etc., etc. Okay, so first of all, the oxidation of a free element is always 0. Okay, so if I have sodium metal, it's 0. If I have calcium metal, it's 0. This also includes our Brinkelhoffs. Remember our diatomic nonmetals. So our Brinkelhoffs, remember when we write them as individuals, we put those 2s on them, and that doesn't get a 2. Okay, and so that means that those in their natural state are an oxidation state of 0. So we'll see when we're doing combustion, and we have plus O2, that oxidation state is a 0. Okay. Any monoatomic ion, that means an ion all by itself in a compound, is going to be the same as its charge. This is especially important or true for group 1 and group 2 metals. So group 1 metals have a +1 charge, but they will also always have a +1 oxidation state when they are in a compound. Of course, if they're by themselves as a free element, it's 0. Okay? In compounds, fluorine is always 1. There are no exceptions to that rule at all. And if you recall, fluorine is the most electronegative, and so it always will gain that electron, so it's always going to be 1. Okay? Oxygen is always going to be a -2 unless it's a peroxide, and then it's a -1. Okay? The thing about a peroxide is most of the time I will tell you it's a peroxide, because there are some things that might be like, for instance, CO2, definitely not a peroxide, that's carbon dioxide, and so in that one, the oxygen is a -2. So I will tell you it's a peroxide with the one exception of you should recognize H2O2, that's hydrogen peroxide, and that's the stuff in the brown bottle you put on your cuts and scrapes. In that case, the oxygen would be a -1 in that case, the oxidation state. Hydrogen is a +1 in covalent compounds, and in metal hydrates, this is a typo. It should be a -1. And so an instance of that, and I think this caught some of you on one of our nomenclature quiz, is something like this. That's sodium hydride. In this case, sodium, a group 1 metal. So rule number 1 wins, and so it's a +1. And then hydrogen is with a metal here, so it's going to be a -1. Okay? And then lastly, why did I know those were the things, is the sum of the oxidation state must be 0 for a compound. And then if you have a polyatomic ion, then the oxidation states must equal the charge. For instance, if I had nitrate, NO3 minus, my total of my nitrogen and oxygen oxidation states need to add up to an overall -1. Okay? So now that I've thoroughly confused you with the rules, let's go on and do some practice ones and see if that doesn't make a little bit more sense. Again, keep these rules handy because we're going to refer back to them. All right, start with a super easy one, and that is lithium. It's all by itself, and so its charge, or its not charge, excuse me, its oxidation state is going to be 0 because it's a free element. Now, if we look at calcium carbonate, I've got calcium, carbon, and oxygen, so I need to find the oxidation state of each one of those. Let's do what we know right off the bat. We know that calcium is a group 2 metal, and so group 2 metals keep their charge as their ionic charge. They keep that as their oxidation state. So calcium is a +2. And then oxygen is a -2. And we know that from the rule that says oxygen is a -2 unless it's a peroxide. I didn't tell you this is a peroxide, so it's not. So now we have to figure out carbon. So we're going to play a tiny bit of an algebra game here. And there are 2 ways you can do this. I can show you the way that I prefer, and that is I take this carbonate out, and hopefully we remember from our polyatomic ions that carbonate is a -2 charge. And so I have to find out what carbon is to make that a -2 charge, okay? So I know that oxygen is a -2, and I have 3. So I'm going to take these 3 times a -2, and I get a total charge of oxygen of a -6. Each individual oxygen is a -2, okay? So we would not change the oxygen. It's a -2. So now I have to look at this and say, okay, what plus a -6 will equal a -2? And so the answer to that is a +4. So that means carbon has to be a +4, okay? If you have no idea what I did, you can always do a very quick -6 plus x is equal to -2, and then we find out that it's +4. Okay? And you don't necessarily have to put the plus signs. You do have to put the negative signs. You don't necessarily have to put the plus signs, but I always do so we can know that we know what that is. The other way we can do that is I can just look at the compound itself and not break anything up. And if you like to do it this way, let's do this one in red. You know that oxygen was a -2, so this is a -6. Carbon is a +2. And so then what do we have to add up to be neutral in this case? So then it would be +4. So that's another way you can do it. However you like or prefer is perfectly fine with me. Okay, so let's do some more examples because that's definitely not enough examples to get this down. All right, so I fully realize that these are different examples than are in your notes, and the reason for that is so you have some extra ones in your notes to try, okay? So you might want to jot these down on the side, on the back or whatever, just find a place to jot these down. So the first one we're going to do is potassium permanganate, okay? And so we look at potassium, whoops, I forgot to say I was going to write, let me go back, okay? So for potassium permanganate, I got KMNO4. And I know that potassium, let's do this over here, potassium is a group 1 metal, so I don't have to question that. It's a +1. And oxygen, -2, because I did not tell you it was a peroxide. So you can count on that being a -2. So now we have to figure out what manganese is. And manganese is a transition metal that can have multiple charges and also multiple oxidation states. So again, I'm going to do my preferred method. And I know that permanganate is a -1. If I didn't remember that from my polyatomic ions, I would know it is a -1 because potassium's a +1 and it only took 1 permanganate to go with it. So I have 4 oxygen, and so if I take those 4 oxygen times my -2, right, I have a total of a -8. And notice I kind of always circle that so I realize that that's not my oxidation state of individual oxygen. That's just my total amount. Okay, so very easily, what plus -8 will make me equal an overall -1, and that is going to be a +7. Okay, so then manganese would be a +7. Again, if you don't like to do it that way, you could have said, okay, this is a -8, this is a +1, so that one would have to be a +7. Same concept, just if you don't want to have to break it out. Okay, so now these next 3 are kind of interesting because they're all just sulfur and oxygen. Okay, so we have sulfur trioxide, not sulfite. And I caught some of you on that with the nomenclature quiz. You saw SO3 and you just wrote down sulfite, but without this charge right here, that is not sulfite without that charge. Okay, so in all of these compounds, oxygen is going to be a -2 in all of them. Okay, so we need to figure out what is sulfur in each one of these compounds because oxygen is always a -2 unless it's a peroxide. So we're going to figure this out. So if I have my SO3, right, and I take this times a -2, that means I have a total of a -6 charge. Well, this is a neutral compound because there is no charge on it, so that means that my sulfur has to be a +6 so they can balance each other out. In the case of sulfite, now I have SO3 with a -2 charge, okay? So still have a -6 total here, so I need to know what plus a -6 is going to equal my -2. And so that, of course, is going to be +4. If you can't just see that, because some kids can just look at it and know right away, and some kids are like, where did I get that +4? You can always do a really quick -6 plus what is sulfur is X has to equal a -2, and then we'll see that X is equal to a +4. All right, and then the last one, now we have sulfur and oxygen as sulfate, okay? And so now still have a total of we still have oxygen as a -2, but now I have 4 of them, so I have a total of a -8. So what plus 8 will equal a -2, and that, of course, is +6. So these two happen to be +6. This one was +4. Okay? The practice worksheet that you picked up today is just practice. You're just going to practice assigning these things because this is a new concept. And so we'll go over it tomorrow in class before we actually do the work that I want to do for this portion of the lesson. And so do your best on that tonight, and then you can ask questions tomorrow and we'll go over the answers. I'm just going to stand up tomorrow and give you the answers to what they are and answer any questions before we go on to the next part of the worksheet that we have tomorrow. The worksheet we have tomorrow is going to include both assigning oxidation states and determining what's being oxidized and reduced, which is the next part of today's lesson. All right, so now let's get into what actually is a redox reaction. First of all, they are always written as half reactions, okay? And they always occur simultaneously, meaning at the same exact time. One doesn't occur before the other. You can't have one without the other. So if you can tell that something's oxidized, something is having to be reduced. Sometimes it gets a little tricky figuring it out, but we will be able to do that, okay? So first of all, what is oxidation? And it is the complete or partial loss of electrons. And so when an element loses its electrons, remember electrons are negative, so let's recall that electrons are negative, and so it's losing things that are negative, so the oxidation state will become more positive. And then the opposite is true for reduction, and reduction is the complete or partial gain of electrons. okay? And so this is where kids get a little bit confused, because the word reduction makes us think that we should be, not gaining something, but what we're reducing is the oxidation state. It will become either less positive or more negative. And the reason I write that both ways is because it will not always become negative. Sometimes it'll just go from like a +4 to a +2, and that's less positive. So that is something that we need to recognize, okay? So this, I've got a cool little acronym in a little bit to help you remember which is which. This unit is actually full of acronyms. All right, so here is an example of a synthesis reaction. If you recall, this looks like this is a synthesis because I have two elements becoming a compound. And so the oxidation state, we're going to look at the oxidation portion first, the half reaction. Of course, that's loss of electrons. So if you look at that, sodium is starting out as a free element, which means it's got an oxidation number of 0. And then it's being ionized, so it loses 1 electron. Now, total electrons it's losing is 2, because I have 2 of them, but each individual sodium is losing 1 electron, okay? So that one is being oxidized. And then on the flip side of that, if you look at the chlorine as a free element is Cl2, and its oxidation number is 0. And of course, it's gaining an electron to become a -1. Again, we're showing 2 here because if you go back to the balanced equation, you've got 2 sodium and then you have 2 chlorines in your Cl2. So each one of those chlorines is gaining 1 electron, okay? So that's how we look at those things. Then we add our half reactions back together, and then we get our overall equation. And notice, whenever you're doing this, you're always going to have your electrons on opposite sides of the thing. So here are the ways that we can remember it. We can remember this as oil rig or Leo the lion goes grr. I never use this one. Sorry, I forgot to tell it I was going to write. I never use this one. Why? Because we are in Texas, baby, so we use oil rig, okay? And oil rig stands for, you can use this one if you want. If you just really like lions, go ahead. But I will usually say, hey, remember oil rig. Oxidation is loss of electrons, and reduction is gain of electrons. So I do want you to take notice of something, and that is sometimes when you're looking at these, if you're looking at equations and you're assigning oxidation states and none of the oxidation states are changing, meaning they stay the same on both sides of the equation, then it's not actually a redox reaction, okay? And so I'm going to give you an example of that, of both what is a redox and what is not, just by looking at the equation. And so let's go with that. So we'll start with one that is a redox reaction. And so we are going to start with, let's see, what do I feel like doing today? Let's just make something up. Oh, let's do a single replacement. So if I have AgNO3 plus, let's go with sodium, right? And then I do that, and I see, will sodium replace silver? And yes, it will. So then it becomes NaNO3 plus silver by itself, okay? And then we're going to do AgNO3 plus sodium chloride, and then, of course, that's going to make a precipitate plus NaNO3, okay? So now we're going to assign oxidation states to everything. So first thing I always do is any free elements, because I know them to be 0. So I'm going to say this one is 0 and this one is 0. Okay. As soon as you see a free element on one side of the equation and it's in a compound on another side of the equation, you can bet your bottom dollar that it is a redox, because it's got to change for sure. Okay. So when sodium is in a compound, it's a group 1 metal, so it's always a +1. Okay, so sodium went from being a 0 to a +1, so that means it lost an electron, so that means it was oxidized. Okay, and then if I look at silver is a +1 over here, and it's a 0 over here, so silver gained an electron, so it is reduced. Now, I don't need to even look at the nitrate, and the reason why is it stays nitrate on both sides, so we know nothing changed. Okay, so in this case, it's going to be called, hopefully you recall, a spectator ion. Okay, so we don't even need to look at that. Okay, but now let's look at the next equation. So the next equation has, which is a double replacement, and so this is going to be a +1 on this side, stays a +1 over here. This is a +1 on this side, stays a +1 over here. Again, nitrate didn't change, so we don't need to look at it. So since there's no change in any of the oxidation states, chlorine, sorry, stayed a -1 and a -1. Okay, so since there is no change on this one in terms of the oxidation states, doesn't mean a reaction didn't happen, it just means it's not a redox. Okay? All right. So then let's finish off this lesson with the agents, okay? The agents of change, if you will, instead of those of you that watch Agents of S.H.I.E.L.D. So a reducing agent, this gets kind of a little bit confusing, but you just need to think they're opposite. The reducing agent is what is being oxidized, okay? So it's what's being oxidized, because what happens is what's being oxidized causes the other item to be reduced, okay? And then vice versa for the oxidizing agent. The oxidizing agent is the substance that is reduced because it causes the other thing to be oxidized. I know it's a little bit confusing. So if we look back at this, which is that equation we used in the very beginning, and we said sodium was being oxidized and chlorine was being reduced. So if sodium is being oxidized, it makes it the reducing agent. And oftentimes we will abbreviate with RA for that. And then since because sodium is causing chlorine to be reduced. And now chlorine is causing sodium to be oxidized, so it is the oxidizing agent. Or OA for short. Okay? So here is just a quick visual to kind of help you understand that they're opposite. Okay, so normally what I do is once I realize what's being oxidized, so we'll go back to that the AgNO3 plus Na, and we said NaNO3 plus Ag, right? And we said that Ag was going from a +1 to a 0, right? So it gained an electron, so I would say Ag is reduced, and it's the oxidizing agent. We'll just go ahead and do that. And then conversely, sodium, remember, went from a 0 to a +1, so sodium is oxidized, which makes it the reducing agent because it causes silver to be reduced. And that is, I believe, where we are stopping the lesson. We will pick up with balancing redox reactions on Monday. All right. Have a great day, and I will be available for help if you need me. Just come by my room.